So today I'm gonna present the work done by Dr. Chitung Liu, our former PhD student, on improving the performance of PLC using Nano-SiO2 or nanosilica-coated limestone composite. So why doing this research? So we know that we have 5 to 15% by weight limestone in PLCs. So the advantages of limestone would be it is a largely available mineral in the world, and the environmental impact associated with the production of limestone powder is pretty small compared to the Portland cement. But there are a couple of disadvantages that just inhibiting adding more limestone and PLC. So one of them would be the very limited reactivity in cementitious media, and also we will get lower mechanical strength and durability when we use larger quantity of limestone in cement-based materials. So another thing that I'm gonna talk about is the application of silicon nanoparticles. We know that they show different performances in cementitious media, including high pozzolanic reactivity and acceleration of cement hydration and microfilling effect among different performances. So with that, using silicon nanoparticles has a couple of advantages. First of all, we can improve the strength, mechanical strength, improve the durability by refining the pore structure, and we will get very, large or high early age strengths, or improvement in the durability and mechanical strength. It is good for like special concretes like UHPC or high early strength concretes that if we want high early strengths, within a couple of days of cement hydration. But there are a couple of disadvantages of using larger quantities of nanosilica or silicon nanoparticles in cementitious media. The most important thing, and is a long-lasting issue, is agglomeration of this type of nanoparticles in cementitious media, because in cementitious media we have calcium ions or couple of multivalent ions, and we have a very high alkaline environment. So with these two, result in agglomeration of silicon nanoparticles. So and then we end up with very, not appropriate dispersion of these particles within the matrix. And another thing is, if we want to increase the quantity of silicon nanoparticles, another issue associated with that is the higher cost of using this material. So as we can see here, we just used, just commercial type of colloidal nanosilica with 300 meters square per gram surface area in DI water and in just a solution of 5 millimolar calcium ions. And you can see that the growth of agglomerates, large agglomerates, we are getting into the micron size, particle size, or aggregate size of silicon nanoparticles by just adding the calcium ions, a small quantity of concentration of calcium ions in the cementitious solution. And you can see that the agglomeration is a big issue with silicon nanoparticles. So how to increase, so the idea of this research, the research motivation is how to increase limestone content while we improve the dispersion of silicon nanoparticles. So the answer that we have for this question is coating limestone with silicon nanoparticles. But we need to know that this coating process should be low cost and should have low environmental impact if we are going to implement that. And it should be pretty simple. So we use the surface characteristics of limestone particles and nanosilica particles. Limestone particles normally, contains, if the conventional or the commercial limestone used in cement industry is calcite. Limestone contains a large amount of calcite, so the surface charge of calcite is positive, and the nanoparticles are negatively charged. So with this tool, we use the we took advantage of electrostatic attraction. So there was some, some steps, in coating nanoparticles, silicon nanoparticles on limestone particles, but the basic idea is the difference in the charge of these two particles, so we can easily just coat the limestone particles with silica nanoparticles. So with that, we made a couple of cement paste samples to see the effect of this, using this composite in cement-based materials. So we use type 1 cement and limestone with 98% purity of, purity, which is the mostly calcite, and 3 microns average particle size, and nanosilica in colloidal form with almost 300 meters square per gram surface area. So we made 3 different sets of samples. The NIT or control sample is the cement with 100% Portland cement. The other one is we just replaced cement by 20% limestone. And we have 2 other cases that contains nanosilica, but in one case we coated nanosilica on the surface of limestone powder we used, and in other case that we only just added the nanosilica particles during mixing. So we just kind of separately adding limestone and nanosilica during mixing. So we used 2 different actually percentages of nanoparticles, as we can see here, 1.4% by weight of total binder and 2.8% by weight of total binder. And the first benefit that we got out of using the nanosilica-coated limestone composite is just we decrease the required sweat plasticizer. To get to the same flow, we defined the same flow as 75 minus plus 5 millimeter using mini slump flow test. So with that, we can see that, it depends on the quantity of nanoparticles, but is almost like 50% reduction of the required sweat plasticizer. So the first benefit we got out of using this composite. The next thing you can see here, the coated nanoparticles and SEM image of the coated nanoparticle on calcite surface. You can see that it is a multi-layer deposits of the nanoparticle, nanosilica, on the surface of the calcite. So if we can see the result of the compressive strengths up to the 28 days of curing. So we actually cured the samples. I forgot to mention that. So with that, you can see that, using 20% limestone just resulted in like almost 20% reduction in compressive strengths at different ages. And when we used nanosilica, either coated or adding separately during mixing, we got improvement in the compressive strengths. But at later ages, we can see that the effect of the nanoparticles just became less because we use very small quantity of nanoparticles, so majority of them just consumed within the first few days of actually reaction. And also we can get very finer pore structure, so the diffusion controlled actually type of reaction or hydration, so would be a little bit harder to proceed. So at later ages, in the samples that we have nanosilica either coated or added separately, we got lower effect at later ages. So as you can see here, during the early age, up to 7 days, we could get very interesting results. So if you use 1.4% nanosilica coated on limestone, we got better results than using 2.8% nanosilica if you're adding that one during mixing separately. So with that, if you are going to use this type of composite for developing special concretes like UHPC or high early age strengths concrete, so that would be really good benefit out of the using this composite. So it is just whatever I mentioned. So we did also calibrated to check the kinetics of cement hydration. And we can see that the addition of limestone, fine limestone that we use, accelerated cement hydration as expected. And we got the loading also of nanoparticles decreased the main peak, as you can see in the as you can see here, the main peak just reduced a little bit, maybe statistically insignificant, but the important thing is when we are coating limestone with silicon nanoparticles, actually we are removing the acceleration effect happening by the using very fine limestone particles. So that's why we got less effect out of the using nanoparticles in the coated state. So, and you can see here, almost statistically insignificant, increase in the cumulative heat, which means, using nanoparticles in the coated state or using it in during mixing separately. So there is no, not significant changes in the hydration kinetic of cement. With that, we get to the measurement of calcium hydroxide content as a representative of the pozzolanic activity within the cement-based material. So we can see that, by using nanoparticles, either coated or just added during the mixing, we got for sure lower calcium or CH content, which is due to the pozzolanic activity. And by using the coated nanoparticles, we can get even smaller CH, which means, due to further, we can get further actually, further decrease in the CH, which is further improvement due to pozzolanic activity. And also we can see that, 20% limestone, if we use that because of the hydration acceleration we can get, so we can get higher CH content due to the improvement of the hydration or acceleration of hydration reaction. So in conclusion, so I would say that if we use silica-coated limestone composite, we can reduce the amount of sweat plasticizer for a specific flowability, so reducing the cost. Also, we can increase the compressive strength, and because due to the pozzolanic, and also we can increase the pozzolanic activity of silicon nanoparticles due to improvement in the dispersion of nanoparticles within the cementitious matrix. And another important thing is if with that we can also increase the quantity of the limestone in PLC, so we can replace more cement with PLC and getting to the greener part of this in the development of PLC cements. And yeah, for sure we are by greening the or by increasing the replacement of limestone in PLC, we can reduce the environmental impact of the PLC. And thank you with that. Thank you, and any question I can take.